Hello everyone. I hope you are having a fantastic day today. I know I certainly am. So this video is a response to a comment that somebody left me. So just to provide a little bit of context, recently I uploaded a video. It was a balancing chemical equations practice problem, and on that video a user by the name of the PR drill left me a comment that reads, "What should I do if the problem only gives me the left side of the equation?" And the example that he gave was the example that's shown on the board here, where we have potassium sulfide reacting with iron 2 nitrate, also called ferrous nitrate. I'm going to be referring to it as ferrous nitrate from here on out, just because it's a little bit quicker to say than iron 2 nitrate. And we have to predict the products. So it's a great question. Thank you very much, the PR drill, for your question. And I would encourage anybody who has any question about anything on their mind to do what the PR drill did. Reach out, leave me a comment, send me a message. There's many different ways by which you can contact me, so I definitely want to encourage that. So I'll start my answer to the question off by saying that this isn't necessarily a balancing chemical equations problem. There is a step in the solution to this problem in which we'll have to balance the equation, but that is just one aspect. There's a lot more to this problem than balancing equations. We need to identify the type of reaction that's going to take place. We need to, it's just a spoiler alert, it's going to be a precipitation reaction, which involves writing a complete ionic equation using solubility rules, writing a net ionic equation, and everything in between. So I'm going to walk you through the entire sequence of steps to sort of solve this. Now, I'm sort of guessing here what the instructions are, because all I have is just this right here, so I'm guessing that it's going to be a precipitation reaction, and we're going to have to write the complete ionic equation and the net ionic equation. So I'll go ahead and get into that now. So we'll start by identifying the type of reaction, and to identify the type of reaction we need to take a close look at these two compounds here. Now, right off the bat, it's becoming immediately obvious to me that both of these compounds, the potassium sulfide and the ferrous nitrate, are both ionic compounds. And how did I know that? Well, that's because ionic compounds will have a metal in addition to one or more nonmetals. And covalent compounds or molecular compounds just have nonmetals only. So potassium, iron, those are both metals. Sulfur, nitrogen, oxygen, those are nonmetals. So we know that these are two ionic compounds. They have a positively charged ion or cation, and they have a negatively charged ion or anion, right? And also notice that there's this little AQ in parentheses after each chemical formula. And that stands for aqueous. You probably already knew that. But intuitively, that just means that instead of actually being held together by the ionic bonds in a solid lattice, these are dissolved in water, which means we really don't have like in the actual sample of material, we really don't have these compounds held together by ionic bonds. Instead, we have potassium ions floating around, we have sulfide ions floating around, ferrous ions floating around, and nitrate ions floating around. So these formulas, as they're written, sort of tend to give the wrong impression, but nonetheless, they are a more concise way of representing this left-hand side of the equation. So anytime you have two ionic compounds reacting together, the reaction that will most likely take place is called a double replacement reaction. I'm going to go ahead and write that down. Double replacement reaction, which means that when these two compounds react, the positive ion of one compound is going to pair up with the negative ion of the other. So you can think of double replacement reactions as, like, let's say you have these two married couples, and let's just say they're pretty loose and liberal when it comes to their marriage vows, but they all, let's say they're all friends and they all just decide we're going to trade partners for a night. That's basically what a double replacement reaction is. Personally, I would never ever do anything like that, but there's people of all different philosophies and walks of life out there, and as long as it's voluntary, I guess I don't have a problem with it. Anyway, let's get back to the chemistry, shall we? So, double replacement reaction, the positive ion of one compound is going to pair up with the negative ion of the other, and vice versa. So what's going to happen here is your potassium ion, where it used to be paired with sulfide, it's going to pair up with the nitrate ion, right? And then vice versa, we have the ferrous ion, the iron 2+ ion here. It's going to pair up with your sulfide ion. So when we go to write the products are going to be the result of that switch, that double replacement, right? Now, in order to write the correct chemical formula for our products, we need to first start by writing out the individual formula for each individual ion, right? So let's start with the potassium ion and the nitrate ion. Potassium ion is going to be K plus, not K2 plus, not K3 plus, or anything but K plus. And the way that you know that is by pulling out your handy-dandy periodic table and observing that potassium belongs to the alkaline metals right there with lithium, sodium, rubidium, cesium, francium, and all of those metals are going to form a cation with a +1 charge every single time. It's unambiguous, right? So that's how I knew that. And let's go ahead and do the same thing with our nitrate ion. Nitrate ion is a little bit more complicated. It's going to be NO3 minus. Not 2 minus, not 3 minus, just minus. How did I know that? Well, it's because I memorized it. Somewhere in your chemistry textbook there should be a table of common polyatomic ions. Nitrate is an especially common one that you should certainly commit to memory. So now that we have our ions written out, we can figure out the chemical formula. So we need to figure out what the subscripts coming after the potassium ion, after the nitrate ion, are going to be. In other words, how many of each of these ions there are going to be in our chemical formula. And the operating principle here is that the compound, as it's written, must be neutral. It can't have a charge on it. So the chemical formula of this compound that results when these two ions come together is going to be the smallest electrically neutral collection of ions, right? And the technique that is the most familiar to people on how to solve a problem like this is called the crossover technique, which involves taking the number of one charge and dragging it down to become the subscript of the other. So in this case, right, there's an understood 1 in front of each of these, this plus and this minus. So we're going to drag that 1 down to become the subscript of the other ion. So since they're both a 1, 1s are generally understood in chemistry. They're not written. They're not really written. They're just kind of understood to be there. We're going to end up with 1 of each of these ions, right? And so our formula of our compound is going to be KNO3. And we need to figure out if this is going to be solid or aqueous using the solubility rules, but I'll save that for a little bit later. For now, I just want to go ahead and do the other example, right? The other product of the reaction. And the other product of the reaction is going to be the result of this iron ion pairing up with this sulfide ion. So the iron, that's going to be Fe. And iron is one of those transition metals that can form more than one different type of cation. Sometimes iron forms a 2+ cation, that's called the ferrous ion. Sometimes it forms a 3+ cation, that's called the ferric ion. And in this case, it's 2+. And what tips you off that it's the 2+ ion rather than the 3+ ion is by looking at the iron species in the reactants, right? So we have this Fe, give me a second here, FeNO3 right? So earlier we established that each of these nitrate ions is -1, right? And according to this chemical formula here, there are 2 of them. So that means the total charge coming from the anions is 2-, right? And we also understand that in order for this to be a neutral compound, there must be no charge, which means that the total charge coming from your cations must balance with the total charge coming from your anions, right? Which means that the iron ion must carry a 2+ charge. So that's how we know that this is a 2+ cation, right? Then we have the sulfide ion. So that's going to be S. And the sulfide ion is going to carry a 2- charge. And the sulfide ion carries a 2- charge for a similar reason as the potassium ion carrying a 1+ charge. It just always does based on its position in the periodic table. Sulfur is right underneath oxygen. All of the nonmetals in that oxygen group called the chalcogens are all going to form anions that carry a 2- charge. So that's how we knew that. So again, to write the chemical formula, we're going to understand that the chemical formula is the smallest electrically neutral collection of cations and anions. So if we use the crossover technique here, right, this becomes a 2 and that becomes a 2, we'll end up with Fe2S2. But again, it's the smallest electrically neutral collection. So anytime you use that crossover technique and that formula can be simplified down, in other words, you can sort of, I guess they would call it like reducing a fraction or whatever. I don't want to get too mathematical here. I don't want to dig back into our algebra as much as, any more than I have to. But anyway, since each individual iron ion cancels out with just one sulfide ion, it's not going to be Fe2S2, it's just going to be FeS. Smallest electrically neutral collection of cations and anions, right? FeS. Okay, so we have the formula for our products written out. Now we have to figure out these guys. We have to figure out whether they're going to be, like, what state of matter they're in, whether they're going to be solid or whether they're going to be aqueous. And the way that we do that is by referring to the solubility rules. I'll go ahead and write that out. Solubility rules. Okay, so you can find solubility rules just about everywhere. They're in your chemistry textbook. Maybe your teacher's nice enough to have given you a handout of them. Maybe there's a PowerPoint slide somewhere that your teacher has shown you that you can grab. I have a video on solubility rules. I'll be sure to drop a link right down there in the description down there to my video on solubility rules. If you want like a PDF file or something, I could send you one, but that's really not necessary because you can find these online or in your chemistry textbook. And if your teacher has a heart, you'll be able to refer to that table on your test, but not all teachers have hearts. Sometimes, you'll have to memorize these things, which can be, it can be a lot. I'll be honest. So if we apply these solubility rules, those are going to tell us whether each of these two ionic compounds is solid or aqueous. Now, if it's soluble, right? In other words, if the compound dissolves in water, that's going to give us AQ. If it's insoluble, if it does not dissolve in water, then it's going to be an S. So if we look at potassium nitrate, right? Just from my memory banks, and I don't have a table in front of me, but just from my memory banks, potassium nitrate, well, we have two, obviously we have two ions, right? And according to the solubility rules, any group 1A metal cation, any alkaline metal cation, when it forms an ionic compound, it's just always going to be soluble. And the same is true for the anion nitrate ion, right? All nitrates are soluble. So this one's actually pretty straightforward because the whole alkaline metal rule that all group 1A metal salts are soluble and all nitrates are soluble doesn't have any exceptions. It's just always soluble. So this one is going to carry an AQ. Now the iron sulfide, or the ferrous sulfide, that's a little bit less straightforward. So if we look at the sulfide ion, right, if we just take a look back at the reactants, we know that the sulfide ion has, in the reactants, has formed a compound that is soluble, right? Because here we have the sulfide ion here in potassium sulfide, and it's aqueous. So we know that sulfide is capable of forming compounds with some cations that the compound ends up being soluble and therefore aqueous, right? But the general rule for sulfides, for S2 minuses, is that they're usually actually insoluble unless they're paired up with an alkali metal, or I think maybe also ammonium, but usually like the alkali metal rule kind of trumps, everything in terms of insolubility. So sulfides are usually insoluble unless they're paired up with an alkali metal such as potassium. Iron, not being an alkali metal, does not fit the exception there. So in other words, this is going to be solid because iron 2 sulfide, or ferrous sulfide, is insoluble in water. It does not dissolve. So right now we have just successfully predicted the products of the reaction, and the equation as it's written now, has a name. There's a name for this type of equation as it's currently written. I'll write it in down here. It's called a molecular equation. Molecular equation, what does that mean? Well, basically that means that the compounds, both the reactants and the products of this reaction, are written as if they exist as molecules, discrete entities held together by chemical bonds, which is not really true in reality, right? Earlier I established that anything with aqueous on it just means that the ions are just kind of floating around in the solution. But the advantage, that's a disadvantage, is that it doesn't really reflect what's actually going on in the reaction mixture. But the advantage of it is that it is a very concise, clean way to write the equation. So it's a molecular equation. Now, a more accurate way to write this would be using what's called a complete ionic equation. A complete ionic equation. And before I go any further, I just realized that I must balance this. It's funny because the original comment was all about balancing, and I almost forgot that I have to balance the equation. So to balance this, I'm not going to go through the whole step-by-step technique where I write everything down and keep my count and everything, because I've done this plenty of times, and I've gotten pretty quick at it. So intuitively I can just look at this and understand that if I leave all of the coefficients as a 1 except for this one and I turn it into a 2, then it's going to balance the chemical equation. And you can go ahead and pause the video right now and confirm for yourself that we have the same number of atoms of every element on the left-hand side and the right-hand side of the equation. So this equation, now that it's now that it's balanced, this is the true molecular equation. But what I was getting at just a second ago is a more accurate portrayal of this would be to write a complete ionic equation. And what does that look like? Well, basically what we're going to do is we're going to take each one of these ionic compounds that exists in the aqueous form, and we're going to bust them up into their constituent ions. And this guy right here, this doesn't dissociate into ions, so we're going to leave that formula alone. But everything else is just going to be blown up, right? So if we start with the potassium sulfide, right, we're going to end up with 2 potassium ions because there's a subscript 2 here, so that means we have 2 of them. So that 2 is sort of conserved, it becomes the coefficient, right? And that's aqueous. Plus, let's get closer to the mic, sorry, one of these sulfide ions, that's S2 minus, also aqueous. And then we have the ferrous nitrate here, where we have Fe2 plus aqueous. These equations get pretty long-winded, I'm sure you can imagine. And then we have the 2 nitrate ions, that's 2 NO3s, NO3 minuses, aqueous. And it's 2 because there's a 2 here, this whole thing in parentheses, there's 2 of them, so that 2 sort of becomes the coefficient in this equation here. So that takes care of the reactants, right? And then on the product side, we have this species here. We have 2 potassium ions, 2 nitrate ions. So I'll go ahead and write in my 2 K pluses. Whoops, kind of wrote the Q before the A, sorry about that. Aqueous. Plus our 2 nitrate ions, that's 2 NO3 minuses, aqueous, and hopefully I don't run off of the page here, plus iron 2 sulfide, ferrous sulfide, and that's a solid. So that is our complete ionic equation. So this equation that you see, this long thing with all of those aqueous ionic compounds busted up into their constituent ions, that is the complete ionic equation. So we can simplify this down further by recognizing that there are some things, some ions that appear on both sides of the equation. And there's a name for these types of ions, and they're called spectator ions. And they're spectators because just like a spectator watches a sporting event without participating in it, the spectator ions are kind of in the mixture, but they don't actually react. They don't actually form new bonds or break any of their bonds or anything like that. They're just kind of along for the ride. Okay? So if we identify the spectator ions, those are going to be the ions that appear on both sides of the equation. And it looks to me like we have our 2 potassium ions on the left and also on the right. So I'll go ahead and mark those. And looks like we also have 2 nitrate ions on both sides of the equation, so I'll go ahead and mark down those. So we're going to simplify this equation down by removing the spectator ions, the ones that don't actually participate in the chemical reaction. And that type of equation that results once the spectator ions are removed has a name, and it's called a net ionic equation. So the net ionic equation is usually like the culmination, the end point of the problem. That's kind of where it all leads to. So if I erase my spectators, you can go away, and you can go away, and you two can also go away. Go on, get out of here. And just to sort of bring things a little bit closer together, I'm going to move my reaction arrow and my ferrous sulfide here all the way to right next to that. So it's going to be FeS solid. So this right here, that is my net ionic equation. So this is usually the step-by-step way that you would go about solving a precipitation reaction equation. So just to sort of wrap up what we did, we predicted the products, sort of drawing upon our knowledge of the periodic table and charges and ions and stuff like that. We predicted the 2 products. We used the solubility rules to determine whether or not they're solid or aqueous. We wrote a complete ionic equation by busting up every aqueous ionic species into its constituent ions, and then we canceled out the spectator ions to arrive at our net ionic equation. So it's a pretty involved process. If you ever are tested on subjects like these, or you're going to be tested soon, you definitely want to practice them over and over again because they can be quite time consuming. You don't want to run out of time on your test because you get stuck somewhere. So that's it. Thank you so much for watching. Thanks again to the PR Drill for that comment. It was awesome. And if you like this video, then feel free to show that you like the video by clicking that thumbs up button. And don't forget to subscribe to the channel, turn those notifications on so you'll be notified the instant my next video is uploaded. Leave me your feedback. I would certainly appreciate it. And I also have profiles on other social media platforms. I've got Facebook, I've got Instagram, I've got Twitter, and I have a Discord server. And if you want to find links to all of those, I'll go ahead and drop them down there in the description, but you can also go to my channel page, youtube.com/BensChemVideos. On the channel banner at the top of the page, the bottom right-hand corner of it has these little icons that have links to my Facebook, Instagram, Twitter, and Discord. All right, so that's it. One more thing, I do live streams occasionally, so keep your eyes peeled for my latest live stream. I would love to have a talk with you, get to know you a little bit better. I think that would be cool. So thanks again, and all right, love you guys. Take care. Bye.